Welcome back to the month of Paradox with Carneades.org. Today we're not going to be doing a 90-second philosophy video because we've made it about halfway through the month. I figured it was about time for us to tackle a bit harder paradox. This is going to be Cantor's paradox and the Continuum Hypothesis. This is a little bit more complicated and definitely a little bit more math-heavy than a lot of the stuff that we usually deal with on this channel. I'm going to do my best to make it accessible to everyone that's watching, but if you get confused, I apologize. Hopefully in the future I'll have a chance to do some more videos on set theory that will make this make more sense. So, imagine that death has come to your door. You're not an Epicurean, so you beg for your life. He takes pity on you and says you can live if you can beat him at 4 games. First game, game 1. I'm thinking of a natural number between 0 and infinity. You have as many guesses as you want, and time will not start again. You're not going to start to age until we're done. Can you guess my number? You know that if you start guessing randomly, you're inevitably going to miss a number. So you have to come up with some system to make sure you hit them all. And you'll never get to the number if you guess randomly. So if you start at the beginning and count every number, you have to get there eventually. By counting every number, 1, 2, 3, and so on, you eventually get to death's number. With 666, by the way, he's not that creative. He congratulates you and gives you the second challenge. Game 2. I'm thinking of an integer. It can be positive or negative now. You have as many guesses as you want, and time will not start again until we're done. Can you guess my number? If you want to try this on your own, pause the video right now, because I'm about to give it away. This is a little harder. There's no starting point, so you can't just count up from 0 again. But if you count out from 0, you think you might have a chance. By starting at 0 and counting out 0, 1, -1, 2, -2, and so on, you eventually get to death's number. It was -666. You suspect there might be an easier way to do this. He congratulates you and gives you the third challenge. Game 3. I'm thinking of a rational number. You have as many guesses as you want, and time will not start again until we are done. Can you guess my number? Once again, pause the video right now if you want to try it on your own. There's a hint coming up in a few seconds, and then I'll give you the answer. Here's the hint. This is even tougher. You know all rational numbers can be expressed as the quotient of 2 natural numbers. And you've already figured out how to list all the natural numbers, so maybe there's a trick you can use. But how can you guess all the pairs of numbers instead of just guessing single numbers? Starting with a half, and then moving to a third, and then a fourth is not going to work because you'll never get any bigger than 1. You start sweating as you realize this might not be possible. You pull out a piece of paper and write. Here's the solution. So, spoilers ahead. 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. But you know listing them this way won't get you anywhere, so you start writing 2 in the numerator, 2 over 1, 2 over 2, 2 over 3, 2 over 4, and so on. 3 over 1, 3 over 2, 3 over 3, 3 over 4, and so on. You keep writing all these numbers, but you realize you're moving in 2 different directions. You can't list all the numbers going down vertically and then list all the numbers going across horizontally because the vertical column is infinite and it'll never end. You stop and think, maybe then, instead of thinking vertically and horizontally, you should start thinking diagonally. You try guessing 1 over 1, 2 over 1, but then, instead of keeping moving horizontally, you go diagonally back to 1 over 2. 1 over 3, 2 over 2, 3 over 1, 3 over 2, 2 over 3, 1 over 4, and so on. By snaking back and forth in this diagonal pattern, you've given yourself something of a starting point up in the corner with 1 over 1, and you're going to keep moving systematically out from that starting point to the point where you're not going to miss a single number. And you'll never get caught in that infinite loop of going down to infinity one way or the other. By using this diagonal method and alternating signs as you did before, 1 over 1, -1 over 1, 1 over 2, and so on, you eventually reach death's number. It was -666.6, repeating. Give him kind of a look But he looks back at you with a malicious look in his skull. He gives you the final challenge. Game 4 in order to cheat death. I am thinking of a real number. You have as many guesses as you want, and time will not start again until we are done. Can you guess my number? Before you get started on this problem, I should tell you you're not going to succeed. You sit and think. The minutes turn to hours. The hours turn to days. The days get so bored, they give up and pass the job on to years. Finally, instead of trying to find a way to list all the real numbers, you decide to prove the task impossible. You know that the set of real numbers can be put into perfect correspondence with the set of all sets. If the latter is uncountable, the former is uncountable. Now, there is a mathematical proof of this. I'm not going to give it here because this is complicated, long, and mathy enough as it is. Maybe I'll offer it in a future video. You could look it up if you're curious. For now, take my word for it. You start listing sets. S1 can be the set of all natural numbers, S2 the set of all even numbers, all prime numbers, all odd numbers, and so on and so forth. And yet you realize that there will always be another set that you'll never list. The set of all numbers n that don't belong to their own set, Sn. What does that mean? Let's see. I've highlighted all the sets where n of Sn belongs to that set. Remember, the set S is going to be made of all numbers that don't belong to their own sets. So right now, the set would be comprised of 4, 5, and 6. 4 is not odd, 5 is not a perfect square, and 6 is not a two-digit number. It does not include 1, 2, 3, or 7, as 1 is a natural number, 2 is even, 3 is prime, and 7 has only one digit. Remember, the set is comprised of all n that do not exist in their own set, Sn. So, S is all numbers n not present in their own sets, and S will never be the same as any previously listed set. It's not going to contain 1, but S1 does, so it can't be the same as S1. It doesn't contain 2, but S2 does, so it can't be the same as S2. It does contain 4, but S4 does not, and so on and so forth. And even if you think that, oh, now we've listed S, we can go on, we'll have listed it, we'll be fine, realize that it just gets counted as S8. S8 contains 4, 5, and 6. And so, if we then would create a new S, it would contain 4, 5, 6, and 8. Because 8 is not contained in its own set, S. The point here is, no matter how you decide to go about listing all of the sets that exist, you will never be able to systematically list them all. Now, we're going to get a little bit more mathematical. We're going to learn some new vocabulary, and hopefully this is making sense. Then we will very soon get to the paradox. The power of any set A is defined as the set of all subsets. A subset is a grouping of some number of members of A, including all of the members of A. So A is a subset of itself, as is any other grouping of any number of members of A. For any set A cannot be put into a one-to-one correspondence, also known as a bijunction, with the power of A, denoted PA. Therefore, the power of A, or the set of all subsets of A, is larger or greater than A. So, the set of all subsets is always going to be greater than that set itself. We're going to use a double greater than sign to denote that a set is greater than another set. So A greater than sign B will mean that A is greater than B, or that B can be put into bijunction with a proper subset of A. A proper subset is a subset of A that does not equal A. So it's a grouping of the members of A that are not all the members of A. And B cannot be put into bijunction with the whole of A. There is no way for us to set up a perfect one-to-one correspondence between all the members of B and all the members of A. If these two things are the case, then A is greater than B. Cantor's theorem goes as follows, and directly from this the paradox will follow. For all sets A, the power of A is greater than A. The power of A cannot be put into a one-to-one correspondence with A. So let's see, Cantor's paradox. There exists a set of all sets, V. This is going to be assumed indirect proof, so you probably can already guess what's going to happen to this premise. If V is a set, so is the power of V. That's the power axiom. It's a common axiom in most set theory. There are sets in the power of V that are not in V. That follows from Cantor's theorem. Therefore, V is not the set of all sets, because there exist some sets that are not in fact members of V. Those sets in the power of V that can't be put into a one-to-one correspondence with V. Therefore, V both is and is not the set of all sets. 1 for conjunction. Therefore, from 1 through 5, indirect proof, the set of all sets does not exist. This is a paradox because that seems really counterintuitive and problematic. It seems like the set of all sets is something that we should be able to help ourselves to. According to Cantor's paradox, it's not. And if the class of all sets is not denumerable or countable, then the set of all real numbers is not either. Those two are of the same power, as we mentioned earlier. Once again, I'm not going to prove this for you here because we're already getting a pretty long video right now, hopefully in a future video. The problem is, if the set of real numbers is not countable, the game cannot be won. You give in and accept your fate. Death once again takes pity on you because you tried so hard for years to prove something that was impossible, and gives you one last chance. If you can prove either that there is no set that is greater than A and less than P of A, or find a set that is, you can still live. But death tells you importantly that no one has ever succeeded at this task. The continuum hypothesis is what death has just asked you to prove. The continuum hypothesis goes as follows. There is no set that is greater than A and less than P of A. So, there's no set that we could fit in. We could create a continuum between A, P of A, P of A, and so on. That there would be nothing else we could stick in between them. The problem here is it's been proven that this cannot be proven in set theory, nor can it be disproven in set theory. There is no way to either show that this is true or false in our current understandings of set theory. That's why it's only a hypothesis. The question for you, if you followed all of that, is Cantor's paradox veridical, falsidical, or antinomious? Watch a new paradox video every single day this month here at Carneades.org. And stay skeptical, everybody.